Hello and welcome back to yet another Prepress video from Fullerton College's Prepress class. This is Ben Kiewit, your instructor. We're taking on, I forget, I lost count. I think it's video number 6 or 7 of too many on our review lecture. So we're looking now at image color spaces. So pixel images can be set to one color, like a bitmap, which is simply just on or off, pixel or no pixel, or depending on the amount of memory you want to assign per pixel, a series of colors could be assigned to each pixel in the image. It can be done in grayscale. Fairly straightforward. That means it's levels of brightness and darkness. It's the next evolutionary step beyond pure bitmap. Beyond that, you have duotones, tritones, and quadtones, which is somewhere between an a cappella band at your local community college, or they could actually be printing things where you use 2, 3, or 4 colors of ink, but not process color. What they really do is they apply extra layers of color on top of each other. You print typically black and, so a duotone would be black and, let's say, sepia. And what that does is make it so that you get a much darker full coverage. So instead of just being 100% black on a grayscale image, the darkest spot is 100% black and 100% something else. So your images can get much darker. It gives a much more dynamic look, although you're still limited to the same number of steps, still only 256 gray levels, but the gray levels are more extreme and it can look really good for black and white photography reproduction. They were more popular before full color printing became a thing and are actually a little bit difficult to get these days because not all file types support a duotone color space. RGB, I think I talked about enough last time, but in case you're just jumping in, it's red, green, blue. That's additive color. That's monitor color on your computer, also your cell phone, also your whatever else is showing you this that's on a screen. Sorry to stop mid-sentence there. I was recording and I saw a really cool bird flying in my backyard. I looked up and it's a western tanager. It's a little yellow bird with black wings and a red head. Excitement around here these days. How fun. Okay, we're back. So RGB is your computer color for monitors and additive. Anytime you're looking at a screen, it's RGB. CMYK, cyan, magenta, yellow, and black. Don't ask me why K means black, just accept that it does. That is our printing color. Those are our printing primaries plus black to let us reproduce as much color as we can. Indexed color is kind of your early, like mid-90s color monitors. Pictures, to make them smaller and easier to look on a computer, would use only 1 byte, 8 bits of information to determine the color of the entire image. Remember that 1 byte, the maximum number you can count to using 8 bits of data of on-off switches and binary is 256. So that means in index color, you have 256 shades of color. It's like a grayscale, but each shade on the scale is a color. So it can either be a system one, kind of like an old Mac OS or Windows pre-XP, like Windows 3, or I can't remember what the number was, Windows 95. Yeah, Windows 95 kind of color palette, where it's what you see on your computer, and it's not all the colors, it's some of the colors, and it kind of looks like all, maybe to you if they mix right in your eyes. Gee, not the best. I ran into one of those live once and it threw me for a loop. It's like I was trying to Photoshop with it and use raster effects to make a thing happen inside this picture they sent me. And it just wasn't working. No matter what I did, it just looked kind of dull and gray. Turns out it was index color. So I couldn't add color to it because the only colors allowed in an index color are the ones already there in the aforementioned index that says these are the colors you can use. Index color is like getting a big box of Crayola crayons and saying, I'm only going to color with these only, no mixing. That's it. So that's index color. Also, I do mean love towards Crayola. That's not a dig at all. Those are awesome. They're the best quality crayons you can get for kid use. Anyways, lab color, LAB. Double check that we're not about to talk about it. We're not. Lab color is not a reproduction model. Everything above this, index, CMYK, RGB, the duotone type thing, and on through in nauseum there, grayscale, that's all about how do you show color. Lab color does not attempt to show you anything. It attempts to map what you see. It's based off of scientific survey data of a bunch of people and what the average human is capable of seeing and what kind of differences in color we notice, how far of into what spectrum are we able to be sensitive to as a creature with our vision system. So lab color is not really a reproduction process. It's a way of saying with pretty good precision, the color I'm seeing is a specific color, and I can say that that is it definitely, and it will be that color again later, and it's not subjective. We now know that is that shade, which is a much more powerful statement than it sounds like. I know it sounds really silly to be excited about the fact that you can determine with some sort of absolute certainty that a color is what it is, but when you start working with, the more you closely you look at color and color management, the farther away from it you actually get. You try to nail it down and say, aha, I found a color, but really you haven't. And lab lets you do that. It lets you at least say, if you chart this thing as L50, A75, B30, you have a color. I pulled those out of thin air, and I'm not sure what that looks like exactly. Just remember that the bigger the A, the more red it is, the smaller the A, the more green. The bigger the B, the more yellow it is, and the smaller the B, the more blue it is. And L is just light to dark. It's kind of like a sphere, a global three-dimensional graph of what colors humanity can see. Cool stuff. Resolution. Resolution is measuring how many dots you have in an image. We are concerned with dots per inch, also known on computers as pixels per inch, because pixels are computer dots. Typically speaking, more is better, less is not great. People will talk about dots per inch, pixels per inch, high resolution, low resolution, and file size to talk about these things. I should also say that if you're trying to print and you have a picture that's under a megabyte, it's probably not going to be good enough to print. But that's just a little, from my experience, kind of moment. Nyquist. So, electrical engineer Harry Nyquist figured out how much signaling power he needed to overcome background noise for radio transmissions, because there's background radiation in other people's transmissions. How powerful of a transmitter do you need to be able to be heard how far away? However, the same theory works for image resolution. So you need 2 pixels per halftone dot when on the final output, and you use this formula. LPI, lines per inch, is how many halftone dots you're using, times 2 to get the number of pixels, times the percent of the enlargement or reduction. Now, typically speaking, you can shorthand this in your brain to, my image needs to be 300 dots per inch at the size it's being used. That being said, that's not always true, because 150 line screen is common for offset lithography, but if you're using something like flexography, you're probably using only 85 dots per inch or less, depending on the crudeness of the system you're running on. So it needs to match the output device and the scale you're going at. Hence, lines per inch times 2 times the percent. But again, you can kind of shorthand in your head 300 dots. Supplied images. A lot of people get these as digital originals now. People take photos using digital cameras and they sell them to stock photo companies. The really good expensive ones are sold by Getty Images, and there's a bunch of other ones out there as well, and a few free ones given away by aspiring artists trying to get themselves a name made. How do you know if it's big enough when you get a picture that someone else took? Well, you can go into image size, a menu in Photoshop, and make sure you're not resampling. And you can just go ahead and see what size it tells you it is, and you can even type in new sizes, and it will tell you what the resolution will be at that size. Digital images are captured 2 ways, although mainly one now: digital camera or digital scanner. They have the same electronic brain in either. The difference is the optics. A camera has the sensor that gets the light, that records the light it sees, behind a series of lenses. How good a lens and how far apart the lenses are changes depending on the quality of the camera and what type of add-on you're slapping onto your DSLR, or how bad your cell phone camera is. Come on, people, stop with the cell phone cameras. Or it's mounted to a fixed plate with a light source that scans back and forth in a scanner. Scanners are not really that that important as they used to be. They're still necessary when you need them. They used to be a universal answer to a universal problem, but now they're a bit more niche, because most photographs are taken on digital cameras. You don't need to scan the developed photos like you used to. Flatbed scanners use charge-coupled devices, CCD. They will scan with their own software, though typically you can also just use Photoshop to do it, and I prefer doing that. Digital cameras. There's a third category not on here, which is that cell phone you bought that said this has a good camera on the packaging to help you buy your cell phone. Point and shoot and cell phones are kind of in the same category. They're consumer level. They have automatic settings and basic functions, and their purpose is to let you take pretty pictures of your vacation that you can then share to Faceagram and Instabook and MySpace. Tom's still my friend. Anyways, you can use those to put stuff there and it will all look fantastic, but it doesn't necessarily do a good job for either with the focus, with the depth of field, with the ability to zoom in a faraway telephoto shot if you're shooting nature or small objects with macro shooting. You want an SLR, single lens reflex. In the old days, these had film. In the nowadays, it's the same basic mechanical thing, except it has an electronic sensor chip where the film used to go. They can either use CCD or CMOS technology as the different types of sensors available in them. So color management is trying to make sure that everything agrees on what color it is. It's hard enough to get people to agree on pizza toppings. It's hard enough to get people to agree on what color something is. You'll say, it looks blue to me, and then they'll say, I don't know. It's not really blue. It's a little more lavender of a blue, don't you think? Because they're seeing a little bit different, or they're more sensitive, or they actually know the names of the colors and you don't. I can fire this right back at people when they're looking at a color, like it's all brown. Like, no. This was an Israeli uniform khaki. This is a World War II British khaki. Don't you see the difference? They're like, no, it's beige. No, those are different shades. Anyways, now that's olive drab painted on tanks in World War II, and that's olive drab painted on tanks during the Korean War. Don't you see it got a lot greener in the 50s? Anyways, doesn't matter what you want to get to. There's someone out there who's not going to agree on what a color is, and that's also a problem with machines as well. The way a camera sees color is different than the way the next camera sees color, which is different than the way that you saw it, which is different than the way the computer saw it, which is different than the way that the printer is going to produce it. So you're trying to make a consistent through line of what does a camera see and how do I get the closest possible representation of that camera image to come out the far end of the whole process, printed and done. Color conversions are made of something called an ICC profile. ICC profiles are a way of looking at every device and saying, well, how does that device show that color? They call it fingerprinting. In fact, it even kind of looks like a fingerprint. That picture of a gamut there, that's a picture of all the colors available. And that's the shape of the visible spectrum for us a little bit. So with a color managed workflow, every device has its own profile. They do this using that lab color we talked about earlier, LAB, which is a map of what colors are. So instead of saying CMYK wants to make a color this way and RGB wants to make a color that way, and the other RGB device wants to make the same color the other way, what you do is you set a target of known LAB values, because those are measured independently of how they're made, and you tell them all to do it. And in the end, you now know, well, when that one tries to make this color, it does this. When this one wants to make this color, it does this. And you find out and you make corrections where they'll automatically change the way they're going to give you the correct thing. Two analogies on that. One, if you've ever driven a car with bad wheel alignment, as I have in my younger years, you find yourself turning your steering wheel kind of halfway to the right to drive straight down the street. I'm exaggerating, but that's kind of how it goes. Or if you had to get a bad shopping cart, let's go with that one. A bad shopping cart at a grocery store that wants to turn hard right and slam into the wall and dump mayonnaise containers, and you don't even want to buy mayonnaise. Anyways, you have to push the cart harder to keep it straight. You push it more on the right to skid it left a little bit. You try to make sure that you're always turning left the whole time you're walking through the grocery store. And it's really annoying, but you can do it because you know it's going to go the other way. You can also say with my example from my own personal life, and I'm part of the problem, not the solution here. My best friend growing up was friends with me and a few other people. And we would have like dorky video game nights and stuff. We'd go play games or whatever. Anyways, if he wanted me and my friend Fred to show up at his house at the same time, he would know after the first time that I'm annoyingly early. I'm going to show up like on time or slightly before time to make sure I'm not late. Fred will roll in a little bit late every time, no matter what. So if my friend wants to have a party or a get together with his friends showing up at the correct time, he wants to have dinner at 7 and then do whatever else we're going to do. So he says, okay, Ben, we're starting at 7:30. Fred, we're starting at 6. And lo and behold, we're both there at 7. So if you know your devices, if one's going to make it way too yellow, you say, guess what? That image is really blue. And then when it adds all the yellow to the image, it balances out to neutral. And that's what ICC Profiles does for you. So here's the color management process before we end right here. for this video at least. Calibration is the first step. Your press needs to do the same thing every time, or you can't fix it. Or I guess you can't color correct. You need to fix it before you do that. In the shopping cart analogy, if that shopping cart is wild and going every which way and slamming into people, pets, children, other carts, piles of apples, comically stacked piles of cans like on TV, knocking everything over in the grocery store because you can't control it at all, well, then you can't just adjust for the mistake. It's just going to be everywhere. You can't account for everywhere. It has to be making the same problem every time. You can adjust for that. So you got to make sure your machine is calibrated and running consistently. Then once it's running the same way every time, then you fingerprint or profile or characterize it, and you make sure, or you find out what is it doing every time now that it's doing the same thing. Let me make my measurements. And lastly, you do that conversion. You figure out, or you have a software figure out the differences that need to be made between what you wanted and what it's giving you so that it will give you what you want. All right, that's it for this video. Stay tuned for hopefully only one or maybe two more to finish out, well, the class.